Hey guys, welcome back to episode 3 of the Digital Logic series. In today's episode, we'll be covering schematics and truth tables, which are what we can use to organize our individual logic gates into useful circuits. Please be sure to like and subscribe if you like this content, as it would help out a lot. And let's just get straight into it. Let's start off by talking about boolean algebra. Basically, what boolean algebra is how you can write out a schematic in terms of an equation, right? Remember how in episode 2 I was talking about how A is input 1, B is input 2, and Y is the output? In Boolean algebra, we will be using these same variables to write out and solve different logic gates equations. Let's start off with the most simple equation, Y equals A. What this means is the output, which is Y, is exactly equal to the input, which is A, right? This equation would represent a simple light bulb, right, that turns on whenever you flick a switch. Right. Let's look at each logic gate as an operation in math. Right. AND gates work as a multiplication of sorts, because if you took A and B and substituted the values of 1 and 0, then 0 times 0 gives you 0, 0 times 1 gives you 0, 1 times 0 gives you 0, and lastly 1 times 1 gives you 1. Right? It's the same whether you use an AND gate or if you use multiplication, they both give you the same answers. For an OR gate, we can use the operator of addition. 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and finally 1 plus 1 equals 1. We write 1 plus 1 as 1, not 2, because the only options in Boolean algebra are either to use the number 0 or 1. So even if you add 1 to 1, that would still be 1 because you can't go any more above that. If you look closely at the order, then you can see the combinations go in order in binary. 0, 0 is 0 in binary, 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. So we're listing out all of the possible combinations in order when you're writing them in a truth table. Next, we have a NOT gate. This does not have a mathematical operator and is instead represented by either an exclamation mark or a line above the relevant letter. So this gate only requires one switch, unlike the other ones, so we can only have two possible outcomes, right? 0 becomes 1 and 1 becomes 0. Next, we have an XOR gate. It's represented by this symbol, which looks like a plus sign inside of a circle. And just for review, an XOR gate will behave the exact same as an OR gate, except that when both A and B are 1, the result will be 0. So let's see the truth table for XOR real quick. When it's 0 and 0, you get 0. 0 and 1 is 1. 1 and 0 is 0. And 1 and 1 is 0. Now you may be thinking, where are the NAND, NOR, and XNOR gates, right? Well, BEDMAS works the same in making logic gates as it does in math, which means that you can do something in brackets and then apply whatever is outside afterwards. This means that a gate like NAND can just be made by combining an AND gate and a NOT gate at the end. So what this would look like is you write AB to symbolize your AND gate, and then you put the NOT gate symbol with brackets to make sure that the negative applies to the result of AB, not just individually A or individually B, right? So then you would get exclamation mark bracket AB bracket. And so NAND, NOR, and XNOR gates don't have operators when writing equations. So let's try a sample problem to hammer home the two new concepts that we've learned, okay? So number 1, the schematic is given, right? Let's do the equation first. So first, we look at the end result, which is an OR gate, right? To get your end result, the first thing that you see is an OR gate. So that means that two different things must be added together to get to the end result, right? Now one of those two things is just C. So we can write something plus C gives you Y, right? Now if we look at the other side, it's a NAND gate. But that can just be written as an AND gate with a NOT afterwards. So it's not something plus c. That gives you y, right? And lastly, we can look at the AND gate, and it's just the switches A and B going into it. So our final equation would be not AB plus C equals y. Now let's work out the truth table for this. So we have the equation of y equals not AB plus C, right? Let's just start out our truth table with A, B, and C. We write, we start off with 0, 0, 0, and then we go down all the way to 1, 1, 1. After that, we break down our equation piece by piece, okay? First up is AB. We multiply all of the values of A and B for each row and just write the result, which should end up looking like this. Next, we flip the results of AB because of the NOT gate, right? So any zeros become ones, any ones become zeros. And we write these results in another column. After that, we go to our final step by adding not AB with the result of C, right? And then we end up with our final column, which will complete the table. So that should do it for today's video, guys, and in the next one we'll be covering K-maps. Alright then, I'll see you guys in the next one. Please like and subscribe if you enjoyed the video, and have a great rest of your day.